Welcome back to Talk Tensors, the show that takes a deep dive into the latest breakthroughs in machine learning research. We break down the complex ideas and explore their real-world implications. And today, we have a really fascinating paper to unpack.
Yeah, this is a good one.
It's called SED2AM, Solving Multi-Trip, Time-Dependent Vehicle Routing Problem Using Deep Reinforcement Learning.
Catchy title.
A mouthful. I know.
It is a bit of a mouthful, but
But don't let that scare you away.
It's really interesting work.
Because the research itself is incredibly relevant to our everyday lives.
Absolutely.
I mean, think about it.
Like anyone who's ever ordered something online.
Or waited for a ride.
Or even just sat in traffic.
Exactly.
This paper tackles a problem that we all experience.
So let's start by breaking down this multi-trip, time-dependent vehicle routing problem, or MTTDVRP, as the paper calls it.
The MTTDVRP.
Because it sounds pretty technical.
It does sound technical, but it's actually pretty easy to grasp once you break it down.
All right, lay it on me.
Okay, so imagine you're running a delivery company.
Right.
You've got a fleet of trucks. Each truck has a limited amount of time it can work each day.
Right. Work done.
And each truck can only carry so much at once.
Makes sense.
Your job is to figure out the most efficient routes for each truck.
Okay, so we're talking about optimizing delivery routes.
Exactly, but there's a catch.
Oh, there's always a catch.
We're not just talking about one delivery per truck.
Okay.
It's multiple trips throughout the day.
So they go out,
They come back,
they reload.
they go out again.
Got it.
Now here's where it gets really tricky.
Okay. Traffic.
Ah, yes, the bane of every delivery driver's existence. And every commuter's too, for that matter.
So traffic conditions are constantly changing.
Right.
Which means that a route that's quick in the morning could be a nightmare in the afternoon.
So you're telling me that this MTTDVRP is essentially a giant moving target?
That's a great way to put it.
Right.
A dynamic problem. And how do traditional optimization algorithms handle that kind of complexity?
Not very well, to be honest.
Oh, really?
Traditional methods, like exact algorithms, they can find the absolute best solution.
But they're slow.
Right, especially when you have a lot of variables to consider.
And heuristics.
Those are faster.
But less accurate.
Exactly. They're like rules of thumb.
So they might give you a decent solution,
Right.
but it might not be the best one.
Exactly.
So what's the alternative?
Well, that's where deep reinforcement learning, or DRL, comes in.
Okay, DRL.
This is a really powerful type of AI.
And it excels at handling these complex dynamic environments.
Exactly. It's like DRL is built for problems like the MTTDVRP.
So DRL is like the adaptable, quick-thinking navigator.
Yeah.
That can adjust to those real-time traffic changes.
Precisely.
Okay, so the authors of this paper have developed a DRL model.
Right.
Called SE2AM.
SE2AM.
And it's specifically designed to tackle the MTTDVRP.
Yeah, it's like they took DRL and they said, how can we make this even better for this specific problem?
I'm intrigued. Tell me more about this SED2AM model.
Okay, so what's really interesting about SED2AM is how it's structured.
Okay.
It's like a brain with two distinct parts.
Two parts?
An encoder and a decoder.
Okay, so the encoder.
That's like the part of the brain that understands the world around it.
In this case, the world is the city with all its roads and traffic patterns.
Right. So the simultaneous encoder learns the relationships between locations on the map.
Okay.
Taking into account how travel times between them change throughout the day.
So it's not just about distances.
Right.
It's about understanding that a route that's quick at 9 a.m. might be a parking lot at 5 p.m.
Exactly.
Because of rush hour.
It does this by co-embedding node features.
Okay.
Like location coordinates and customer demands.
Right.
With edge features.
What are edge features?
The main edge feature is the time-dependent travel time between those locations.
Interesting.
Just like you said, it's not just distances. It's like how long does it actually take to get from point A to point B at different times of day.
So the encoder is essentially building a dynamic map of the city.
Right.
That evolves throughout the day.
Exactly.
Based on traffic patterns.
Yeah.
It's like having a Waze app that can predict the future.
That's a great analogy.
So once the encoder has built this dynamic map,
yeah,
the decoder comes into play.
Right.
This is where things get really interesting.
This is where the action happens.
Okay, tell me more.
So SED2AM uses a dual decoder.
Dual decoder.
Two action centers, if you will.
Okay, two action centers. I'm intrigued. Break it down for me.
Okay, the first part is the vehicle selection decoder.
Vehicle selection decoder.
At each step, it decides which vehicle from the fleet is best suited to take on the next trip.
No.
It considers factors like the vehicle's remaining work hours and its capacity.
So it's like a super efficient dispatcher.
Exactly.
Constantly evaluating which vehicle is in the best position to pick up the next delivery.
Right, and then you have the trip construction decoder.
Construction decoder.
This one figures out the optimal sequence of stops for the chosen vehicle.
Okay.
And here's the key.
Yeah.
It's continuously adapting to those real-time traffic changes.
Oh, so it's rerouting on the fly, just like a navigation app.
Precisely. It's like having a little AI driver in each truck.
That's amazing. So essentially, one part picks the best vehicle.
Right.
The other part plans its route. And they both work in sync,
They have to.
taking into account the constantly changing traffic.
It's a beautiful dance of optimization.
It does sound incredibly efficient.
It is.
But does it actually work in practice?
That's the million-dollar question.
Right.
And the answer, based on the paper's findings, is a resounding yes.
Really?
They tested SED2AM using real-world data from Edmonton and Calgary in Canada.
Okay, real-world data. That's always a good sign.
And what's remarkable is that it not only outperformed other DRL methods, but it also beat traditional algorithms.
Wait, hold on. It outperformed traditional algorithms.
It did.
Like ant colony optimization and genetic algorithms.
Those two.
Those have been around for decades
I know.
and are considered quite effective.
They are.
So how did SED2AM manage to beat them?
It all comes down to how SED2AM incorporates time-dependent information directly into its learning process.
Right, so it's not just about finding the shortest route on a static map.
Nope.
It's about understanding how those routes change throughout the day.
Exactly. It's that dynamic map we talked about.
Right, the encoder's ability to understand how traffic patterns change throughout the day.
That's the game changer.
Because it allows the decoders to make much smarter routing decisions.
Right.
Leading to significant savings in travel time and overall efficiency.
It's all about working smarter, not harder.
Okay, that makes sense. So it's not just about speed, but also about finding better routes that take into account real-world traffic conditions.
Yeah.
But I'm still curious, what makes this model so much better than previous DRL approaches?
Right.
Because it's not the first one to try tackling this problem.
You're absolutely right. It's not the first. But the authors of this paper did a fantastic job of identifying the limitations of those previous approaches.
Okay, so they learned from the mistakes of the past.
Exactly. They highlighted 3 key shortcomings.
Okay, let's hear them.
First, the difficulty in capturing the dynamic nature of travel times.
Right, so those previous models weren't really good at dealing with traffic that changes throughout the day.
Exactly. Second, the inability to directly associate trips with specific vehicles.
Okay, so they were treating all the vehicles as interchangeable.
Yeah, which is not realistic in the real world.
Right, different vehicles might have different capacities or different availability.
Exactly. And third, the lack of sufficient vehicle-specific state information.
So they weren't taking into account things like the vehicle's remaining fuel or its current location.
Right.
So SED2AM was designed specifically to overcome these limitations.
It's like they took all the lessons learned from those previous attempts.
Yeah.
And they said, okay, let's build a model that does it right.
That's really insightful. It shows how critical it is to understand the shortcomings of previous work before you can truly innovate.
Absolutely.
So they built a model that addresses those limitations.
Yeah.
They tested it on real-world data.
Right.
And it outperformed the competition.
It did.
Pretty impressive.
Yeah, it's a really impressive piece of work.
But what does all this mean for our listeners who maybe aren't deep into the world of machine learning and logistics?
Great question.
Why should they care about this research?
Because it's not just an academic exercise.
Okay.
This research has real-world implications for all of us.
So how does it affect us?
Well, we're talking about optimizing delivery fleets.
Okay.
Making public transportation smarter, even improving the efficiency of waste collection.
So it's not just about algorithms and data.
Nope.
It's about making our cities run smoother, greener, and maybe even a bit less stressful.
Definitely.
Imagine a future where your deliveries always arrive on time.
Yeah.
Garbage trucks aren't clogging up rush hour.
Right.
And public transit actually gets you where you need to go when you need to get there.
It's a beautiful vision.
It is. And this research is a step towards that future.
It is.
What I find particularly fascinating is the paper's discussion of SE2AM's ability to generalize.
Oh, yeah, that's a key point.
Generalize meaning it can be applied to other cities or scenarios.
Exactly.
Beyond just Edmonton and Calgary.
They found that SE2AM can be trained on a smaller problem.
Okay.
and then applied to a larger one.
Without losing its effectiveness.
Without missing a beat.
So that suggests it could potentially handle even more complex logistical challenges in the future.
Right.
Maybe even on a global scale.
Potentially.
But before we get ahead of ourselves and start speculating about the future.
Let's take a step back and look at how this research fits into the historical context of vehicle routing problems. Yeah.
I always find it helpful to understand where a particular research paper sits in the larger timeline of a field.
Right.
It gives you a better appreciation for how far we've come.
Absolutely.
So let's dive into that history. I'm ready when you are.
All right, let's do it.
Okay.
So the history of vehicle routing problems, it's actually quite fascinating.
Oh, I bet it is.
It dates back decades.
Wow, decades.
And early attempts to solve these logistical puzzles relied heavily on mathematical formulas.
Okay.
And what are called exact algorithms.
Exact algorithm.
The goal was to find the absolute best solution.
Right, the most efficient route possible.
Exactly.
But these methods quickly ran into limitations.
Yeah, they did.
When faced with real-world complexity.
Because the real world is messy.
It is. So tell me more about those early attempts.
Okay, so imagine trying to calculate the shortest route for 100 delivery trucks.
100 trucks, wow.
Each with multiple stops.
Okay.
In a city with thousands of roads.
My head's spinning already.
Even with powerful computers.
Yeah.
It could take days or even weeks
wow.
to find the optimal solution using exact algorithms.
So not exactly practical for real-time application?
Not at all.
I could see how that would be a problem.
Yeah.
So how did researchers move beyond these limitations?
Well, faster computers definitely help.
Okay, so Moore's law to the rescue.
To some extent, but the real breakthrough came with the development of heuristics.
Heuristics.
And what we call meta-heuristics.
Meta-heuristics, okay.
These are essentially clever shortcuts or rules of thumb that guide the search for a good solution.
So instead of aiming for perfection,
right,
which is computationally expensive.
Very expensive.
These heuristics prioritize finding a good solution quickly.
Exactly.
So it's like navigating a city without a GPS.
Yeah.
You might use landmarks, traffic patterns,
right,
or even your intuition to find your way.
You know, sometimes you just got to go with your gut.
It may not be the absolute shortest route, but it gets you there in a reasonable amount of time.
Exactly.
So heuristics are like the street smarts of optimization algorithms.
I like that.
While exact algorithms are more like trying to meticulously plan every single step.
Exactly.
Can you give us some examples of these clever shortcuts?
Sure. Some of the most famous heuristics for vehicle routing problems include the Clark and Wright savings algorithm, which focuses on minimizing the total distance traveled by combining routes efficiently.
Makes sense.
And then there's the nearest neighbor algorithm.
Nearest neighbor.
Which, as the name suggests, simply chooses the closest unvisited destination at each step.
Okay, so it's like saying, all right, I'm here.
Yep.
What's the closest place I need to go?
Boom.
Let's go there.
Done.
These methods are much faster than exact algorithms.
Oh, yeah. Way faster.
But they often produce solutions that are further from the optimal.
Right. It's a trade-off.
So it's a trade-off between speed and accuracy.
Exactly.
But you also mentioned meta-heuristics. How do those fit into the picture?
So meta-heuristics take the concept of heuristics a step further.
Okay.
They're essentially higher-level algorithms that guide the search process by combining and adapting different heuristics.
So it's like having a master navigator.
Yes.
Who knows when to use a map.
Right.
When to rely on landmarks and when to simply ask for directions.
Sometimes you just got to swallow your pride and ask for help.
I like that analogy. So it's about choosing the right tool for the job.
Exactly.
Depending on the situation.
You got it.
What are some examples of these meta-heuristics?
So some popular examples applied to VRPs include genetic algorithms.
Okay, genetic algorithms.
Which mimic the process of natural selection to evolve better solutions over time.
So it's like survival of the fittest, but for algorithms.
Exactly.
And then there's ant colony optimization.
Ant colony optimization.
Which is inspired by the foraging behavior of ants.
Right. Those little guys are amazing at finding the most efficient paths.
It's fascinating how we often look to nature for inspiration when designing algorithms.
I know. It's like nature has already solved so many complex problems.
Yeah.
We just need to figure out how to learn from it.
First, the human brain analogy with SED2AM.
Right.
Now ants and evolution.
Nature is full of brilliant solutions.
It's a reminder that nature has already solved many complex problems. And we can learn a lot by studying its methods.
Absolutely.
But let's get back to the timeline of VRPs.
Okay.
Where does deep reinforcement learning fit into this historical journey?
So DRL is a relatively recent addition to the VRP toolkit, emerging in the last decade or so.
So it's the new kid on the block.
It is.
But it's already making waves.
Big waves.
And it's a fundamentally different approach.
Right.
It leverages the power of neural networks.
Those artificial brains.
To learn from data and improve its performance over time.
It's like giving the algorithm the ability to learn from its mistakes.
So it's constantly getting better.
Yep.
Unlike heuristics, which rely on predefined rules.
Right.
DRL models can adapt and evolve their strategies.
Exactly.
Based on the specific characteristics of the problem they're trying to solve.
It's like they're constantly tweaking their approach.
Okay, so DRL is like the learn-as-you-go approach to VRPs.
That's a great way to put it.
Kind of like how a human driver gets better at navigating a city the more they drive around.
Precisely.
And that's why DRL is so well suited for the multi-trip time-dependent vehicle routing problem.
Right.
The MTTDVRP.
It can handle those complex dynamic environments
where traditional methods struggle.
They really do.
Now, before we move on to our novel notions segment,
yes,
where we'll explore some potential extensions of this research.
I'm excited for that.
Let's do a quick recap.
Good idea.
So we started by defining the MTTDVRP.
Right.
And explaining why it's such a challenge for traditional optimization methods.
Because it's complex and dynamic.
Then we dove into the details of SED2AM.
That awesome new DRL model.
This new DRL model that's designed to tackle this problem head on.
Head on.
We talked about its innovative encoder-decoder structure.
Right.
Its ability to handle real-time traffic changes.
Like a champ.
And its impressive performance compared to other methods.
It's a real winner.
And we just took a journey through the history of VRPs.
A whirlwind tour.
From those early exact algorithms.
The pioneers.
To the rise of heuristics and meta-heuristics.
The clever shortcuts.
And finally to the emergence of DRL as a powerful new tool in this field.
The new sheriff in town.
It's been quite a ride.
It has.
Anything else we should highlight before we move on to the more speculative part of our discussion?
I think it's worth emphasizing that while SE2AM has shown remarkable results, the authors are very clear about the fact that this is still an active area of research.
So they're not claiming to have solved the problem completely. They're acknowledging that this is just one step forward in a larger journey.
It's all about continuous improvement.
And that's the beauty of scientific research.
It is.
It's an ongoing process of discovery, refinement, some collaboration.
It's a team effort.
Speaking of discovery and refinement,
yes,
I'm eager to hear your thoughts on how this research could be extended. Or applied in new and innovative ways.
I've got some ideas.
You've been teasing these novel notions all episode.
I have.
And I'm ready to dive in.
All right, let's get speculative. Remember, these are just thought experiments, just to spark some discussion and exploration. So we've already talked about how SED2AM can adapt to real-time traffic changes.
Right.
But what if we could push that idea even further? And create a system that not only predicts traffic, but also actively influences it.
Now you're talking about playing traffic god. I love it.
It's a bit out there.
But seriously, how could we possibly control the ebb and flow of vehicles in a city?
It might sound far-fetched.
It kind of does.
But think about the tools we already have at our disposal.
Like what?
Traffic lights. Variable speed limits, even congestion pricing systems. What if we could use AI and machine learning to manage these tools in real time, optimizing traffic flow?
Based on predicted conditions.
Exactly.
And overall city goals.
It's about taking a more proactive approach.
So instead of just reacting to traffic jams. We could proactively prevent them from happening in the first place?
That's the idea.
That would be huge.
It would be a game changer.
But wouldn't that require a massive amount of coordination and control?
It would.
And what about individual driver freedom?
That's a good point.
Wouldn't people resist being dictated to by a computer algorithm?
Those are all valid concerns.
Yeah.
This wouldn't be a simple technological fix.
Right.
It would require careful consideration of the social, ethical, and privacy implications.
Okay.
We'd need to ensure transparency, fairness, and accountability in how such a system is designed and implemented.
So it's not just about the technology itself.
It's about the bigger picture.
It's about how we use it.
Exactly.
But I do think the potential benefits are worth exploring. It's a complex problem.
Very complex.
But one that deserves our attention.
Absolutely.
After all, traffic congestion is a major issue in cities around the world.
It is.
With significant economic, environmental, and social costs.
It affects us all.
If we could find a way to manage traffic more intelligently, using AI and data-driven approaches, it could have a transformative impact on urban life.
It really could.
Okay, so that's one novel notion.
Right. Playing traffic god.
What's your second one?
Okay, so my second novel notion also builds on an idea we've already touched upon.
Yeah.
Vehicle-to-vehicle communication.
Right. We've discussed vehicles sharing data about traffic conditions.
Yeah, but what if they could also share information about their intentions?
Hold on. You're suggesting that cars could start gossiping about where they're going. Next thing you know, they'll be complaining about their drivers and bragging about their fuel efficiency.
Not quite.
Okay.
But imagine a scenario where a car approaching an intersection could signal its intended path to other vehicles in the vicinity.
So like turn signals, but on steroids.
Exactly.
Yeah.
Or a delivery truck could broadcast its upcoming stops,
Oh.
allowing other vehicles to plan their routes accordingly.
Interesting.
This could lead to a much more efficient and predictable traffic flow.
Because vehicles would be able to anticipate each other's movements
Yep.
and avoid potential conflicts.
It's all about communication and collaboration.
I could see how that would work in theory.
Yeah.
But wouldn't it be incredibly complex to implement?
It would be challenging.
How do you ensure that all vehicles communicate effectively?
Right.
And that the information is reliable and secure?
You're hitting on some of the key challenges.
Okay.
It would require collaboration between car manufacturers, technology companies, and policymakers.
A lot of moving parts.
There are.
But again, I think it's a fascinating avenue for research and development.
It is.
Now, before we wrap up this episode,
Okay.
I want to leave our listeners with a final thought-provoking question that builds on the research we've discussed.
I like it.
So the paper focused on optimizing delivery routes and minimizing travel time.
Right.
But what other applications of this research do you envision?
Oh, that's a good one.
What other fields could benefit from this type of AI-powered optimization?
That's a great question to ponder.
Yeah.
We've already talked about traffic management.
Right.
And even hinted at some potential applications in areas like waste collection and public transportation. But I think the possibilities extend far beyond that.
Like what?
Take healthcare, for example.
Healthcare. That's not something I would have immediately thought of.
Really?
How could a system like SED2AM be used to optimize healthcare operations?
So imagine a hospital using SED2AM to manage the flow of patients, doctors, nurses, and equipment within its facilities.
Okay.
You could optimize the scheduling of appointments, the allocation of resources, even the movement of patients between different departments,
Interesting.
all while taking into account real-time factors like patient arrivals, emergency situations, and staff availability.
So it's like applying the same principles of dynamic routing and optimization,
Exactly.
but to the complex world of a hospital.
It's about bringing that same level of efficiency and intelligence to healthcare.
That's an intriguing idea.
It is.
It could potentially lead to shorter wait times,
Right.
more
Yeah.
efficient use of resources,
Mm-hmm.
and ultimately better patient care.
That's the goal.
But wouldn't that be incredibly sensitive data to work with?
You're absolutely right. Privacy and security would be paramount in any healthcare application.
Of course.
But if done responsibly and ethically,
Okay.
I believe this technology has the potential to revolutionize how we deliver healthcare.
I'm starting to see a pattern here.
What's that?
You seem to think that AI can revolutionize pretty much everything.
Maybe I'm a bit of an optimist.
But hey, optimism is a good thing,
It is.
especially when it comes to the potential of AI to make our world a better place.
I couldn't agree more. Yeah, I do have a lot of faith in AI's potential, but it's important to be mindful of the risks too.
Of course, technology is a tool, and like any tool, it can be used for good or for evil.
Exactly. It's all about how we choose to wield it.
That's a good point. For now, let's stay focused on the positive potential of SED2AM.
Okay.
It's fascinating to think how a model designed for delivery routes could be applied to something as complex as a hospital.
Right. It really speaks to the versatility of these AI techniques.
It does. It makes you wonder what other fields could benefit from this kind of thinking. We've touched on healthcare, but what about something like manufacturing or supply chain management?
Oh, yeah, those are great examples.
Those industries rely heavily on logistics and efficiency, right?
Absolutely. In fact, I think those are prime areas where SE2AM's capabilities could really shine. Imagine a factory floor with multiple robots working together to assemble complex products. SE2AM could be used to optimize the movement of those robots, ensuring they're always in the right place at the right time to minimize downtime and maximize production efficiency.
So instead of delivery trucks navigating city streets, we're talking about robots zipping around a factory floor, carefully choreographed to work together seamlessly.
Oh, exactly. It's like a ballet of efficiency.
I love it. And it doesn't stop there. Think about supply chain management. A global network of suppliers, manufacturers, distributors, and retailers all trying to move goods from point A to point B as quickly and cost-effectively as possible.
Right. Global supply chains are incredibly complex.
Now, that's a logistical challenge if I've ever heard one. So many moving parts, so many potential delays and disruptions. How could SE2AM help with that?
Well, a system like SE2AM could be used to optimize the entire chain, taking into account factors like transportation costs, inventory levels, production schedules, and even unexpected disruptions like weather events or port closures.
Wow, so it's like having a crystal ball that can predict the future of your supply chain.
Yeah. Not quite a crystal ball, but it's definitely a powerful tool for forecasting and planning.
And it could help companies make smarter decisions about where to source materials, how to route shipments, and when to adjust production plans to minimize cost and maximize efficiency.
Exactly. It's all about making data-driven decisions.
It sounds like SED2AM could be the ultimate tool for any industry that relies on complex logistics and dynamic environments.
I think so. It's like having a super intelligent conductor orchestrating a symphony of efficiency.
That's a great analogy, and it highlights the potential of this research to transform not just individual industries, but entire economies.
It's about taking a systems-level approach to optimization.
This has been an incredible journey. We started with a single research paper and ended up exploring the future of AI-powered optimization in everything from healthcare to manufacturing to global supply chains. It's amazing to think about the impact this technology could have on our world.
It truly is inspiring, and that's what I love about exploring these novel notions. It allows us to step outside the confines of current thinking and imagine what might be possible in the future.
And that, my friends, is what Talk Tensors is all about. We don't just summarize research papers, we unpack them, analyze them, and explore their potential to shape the world around us.
We encourage all of you listening to check out the show notes for a link to the full research paper on SED2AM. It's a fascinating read, even if you're not a machine learning expert.
And if this episode has sparked any novel notions of your own, we'd love to hear them. Share your thoughts with us on social media or drop us an email. Until next time, keep those brains buzzing and stay curious.